recording. Move back to this thing. Do that. Okay. And then we hit you. Alright. Okay. Let's get going. So, let me say this first. That way, you guys can think about it while I'm lecturing and be distracted. So, you know those AP questions, the topic questions that are completion grades? I talked about this before. They're completion grades. I want you to do them, look them over, watch the videos. All right. Right now, the participation for that is pretty middling. A lot of people are doing them, but kind of sparingly. Like, all of a sudden you remember, oh yeah, I need to do those, and then do a bunch of them. Maybe it's because you forget them. I don't know. So my thought is, do one of two things. Either one, because they're free points, right? Yeah. It's free real estate. So, you can sit there and I was thinking about assigning all of them at the very beginning of the unit, that you do them as we learn, right? That's one way of doing it. That's about 30 points of free points if you want to do them. Problem, if you don't do them, that's 30 zeros that are in there. You see what I mean? So, is this going to be a situation where it's going to the rich helping the rich while the poor get poor, or is this going to actually help out the people that maybe need a few free points? So, that's why I'm going to put it up to a vote. You guys get to decide. I can either keep doing what I'm doing, put a couple out here and there as I see fit, or I'll put all of them out, and then you can go through and do all of them. That's more points. But then again, if you don't do them, more zeros. I'm sorry, I couldn't hear you. Yeah. If you go through, look on Canvas, on assignments, the section is called like video questions or something. You'll see Yeah, so far there's only been one for Unit 3. Yeah. We've only had one for Unit 3 so far. So, that's the thing, right? I was going to go through and assign them, but then again I was like, well, I need to put this up to a vote first to see if you want all of them?
Oh, yeah, just put all of them.
Or just a couple? So, I mean, that's the thing, right? You guys get to decide. So, I'll take the vote at the end, think about it. Oh, wait, whoa, I always like this. Also, if you want to give an impassioned speech for one side or the other, feel free to, I'll give a moment for comments. All right.
Are there any rules against speed running all of them?
Say what?
Are there any rules against speed running all of them if you assign them all at one time?
No.
Okay.
Honestly, if you wanted to do that and answer C on all of them and leave all the free response blank, sure.
Oh, I won't leave all the free response blank. I'll take the side analysis. Not these idiot answers horrible.
Well, here's the thing. Here's the thing. I would hope you don't do that. That's kind of like saying, like, oh no, I totally studied, and all you did was just stare at your notes and not actually read them.
I didn't study.
You know what I mean?
I didn't study. Don't worry.
Yeah. So it's one of those things where it's like, I'm doing this to make sure that you at least, at the very minimum, your eyes glanced over the problem to find C. If you want to do that,
You thought about it a little bit.
it's not going to help you much on the exam, which guess what, is going to be worth a lot more.
One neuron.
Right? So, it is basically just a way to make sure you have your at least kind of study. Yeah. I wouldn't suggest that though. I'd actually take some time. Okay. Alright, there's that. What else is there? So last time we were talking about ideal gas law, right? What's the ideal gas law?
Yeah.
PV, N, R, T. What's P?
Pressure. Volume. Number of moles. Temperature. That's just, what is it?
Gas constant.
The super
Gas constant. So if I give you 4 of them, can you find the 5th?
Yes.
Yeah. That's pretty easy, right? Just algebra. Okay. Lab is going to happen on Thursday, I think. So, lab's going to be on Thursday. Thursday's a fun lab. I like it because what we're going to do, like if I want to figure out what P is, what do I need? The rest of this, right? Okay. The lab on Thursday is called Finding R. So how do we know that R is 0.08206?
By what other?
It's like pi.
It's like pi, right? It just is. But how do we know it just is? How do we get that number? Why not?
What the other measurements are measured by?
Yep. So what we're going to do is we're going to figure out the pressure of this place, the volume of the container, number of moles which are in there, and the temperature of it. Put it all together and you will get R. Now here's the cool thing. This is one of my favorite labs because you get so close to R, it's ridiculous. It's great. It's one of those labs that just works. You know what I mean? I always hate a lab where it's like, all right, so you should get 2.4. I got 3.9. Close enough. Moving on. Right? No, this one, I wouldn't be surprised if you get like 1% error. Like you get, it's nice. And if you don't, that's fine too. All right. So there's that. I have an assignment, a PV equals NRT assignment for you on Canvas. If we finish early today, you'll have a bit of time to work on that. Any other questions, comments, or concerns? All right, let's talk about kinetic theory. The kinetic gas theory. Kinetic gas theory is, or just kinetic molecular theory. It's the fact that molecules tend to move. Actually, before I do that, I forgot to mention this. It's Monday. So, you have the ideal gas law. There's also this is called there's partial pressure. Partial pressure is pretty easy. The pressure that oxygen is putting out, plus the pressure that nitrogen is putting out, plus argon, plus H2O, plus CO2, equals the total pressure of the mixture. It's pretty simple, right?
So it just all adds up.
It all adds up.
That's nice.
So, partials equal total. So you can do some things on this, right? If I know the pressure of nitrogen, argon, water, CO2, and the total pressure, can I figure out the pressure of oxygen?
Yes.
Yeah, right? So, there's that. That's how one would go about it. If you're a math type person, here's the thing. The pressure total equals P1 plus P2 plus P3, so on and so forth. So there's that. All good? Pretty straightforward concept. Alright, now let's get into freaking kinetics, or the kinetic molecular theory. Kinetic molecular theory, so let's kind of roll through this. Molecules move, right?
Yes.
Particles move, atoms, molecules, all that. Movement has to do with temperature, okay? So, if you have something that is a solid, but it's really hot, what is the molecule doing? Moving, but how is it moving? There's 3 different words up there that we're going to be using. So, vibrational. So, if you're solid and you're hot, you're vibrating. Okay? You're vibrating. Okay? So, if something is solid, but it's cold, you're vibrating a little bit, not very much. If you are at 0 Kelvin, what's called absolute zero, how much are you moving?
No,
0.
Technically, you don't exist.
Yeah. Theoretically, how much are you moving?
No.
None. 0. Because of that, you can never reach absolute zero because you can't stop motion like that. There's that. Okay. So let's say that you're a part of a solid. You have a little bit of intermolecular forces going on, right? Okay, a little bit of an intermolecular force, and you're vibrating a little bit, but hey, nothing's too bad, right? You're a polar compound. All of a sudden you start heating up. What happens? You vibrate more. Oh no, you broke that intermolecular force, and now you are a, what? Not a solid, but a liquid. That's how you go from a solid to a liquid. Okay? Because you are vibrating to the point where you are breaking those intermolecular forces. Now, when you are a liquid, not only do you vibrate, but you also rotate. So your water is sitting here doing this. Okay? Now, this is what water looks like. If you're, I'm not going to do vibrating with this, but you're rotating, right? So what are the intermolecular forces doing? Right? Making, breaking. Breaking. Oh no. Making, breaking. Making, breaking. Right? You're making and breaking all the time, right? So it's keeping these guys kind of close together, right? So I can do it this way. So a little bit of a force. I'm rotating. Now that happens again. It kind of keeps me close by, right? Pulls me in a little bit closer. Keep going. Rotate. Keeps me a little bit closer. Go on. So on and so forth, right? Okay. Now what happens if you heat up water? What's going to happen to the rotation? Rotation's going to go faster. Less of a force, right? There's not a whole lot of grabbing going on. And if you go fast enough, what's eventually going to happen?
You're never going to touch.
I start drifting away. Oh, and now it's not even anywhere near me, right? So what does that mean? You're going from a liquid to a gas. See how that works?
Yeah.
Does that kind of make sense? Gonna see what molecules are doing down in molecule town? Now, think about this. Lots of intermolecular forces on a water, right? Strong intermolecular forces, right? Let's take another up, down, up. Yeah. All right. Which one do you think is going to have more intermolecular forces?
One on the right.
This one, right?
Yeah.
That's sugar. So what phase is sugar in? Solid, liquid, or gas? Solid. Liquid, right? Can you melt sugar?
Yeah.
Sure. You just have to shake this to the point where these boys don't have those hydrogen bonds or dipole forces anymore. Okay? Boys are breaking up. Exactly. And then it starts to melt. You can melt sugar. You guys did it before. Right? All good so far?
Rapidly and
Rapidly, and then it got fast.
yeah.
All right. We all good with that so far? Concepts of how to go from a liquid to a solid to a gas. By breaking those intermolecular forces, because we're heating them up. Heating up means that you're adding more kinetic energy, more speed to it. Okay? Now there's a difference between kinetic energy and speed. We'll get to that in a little bit. Okay. The physics people out here are about to jump down my throat. But speed is not kinetic energy, is it? No, it is not. We'll get to it. All right. So, this is a nice little molecular representation of a gas, because it shows several things. One, it shows that they're moving. So it shows that translational motion, right? 2, it shows them bouncing off of the container, right? That is indicative of the pressure. The pressure is how much force, total force, you have against the edge of the container, okay? So, the thing is that do the gas particles just continually press up against the container? No, they're just bouncing off, right?
Yeah.
Wouldn't be the first time. So, you're just continually bouncing off of the container, right?
Yeah. It's funny, as you said, they don't just lean up against the wall. There was just one that was.
No, this is the thing though, right? It just didn't have a whole lot of kinetic energy at that moment, right? You just had it. So, you need to hold this, thusly. Thank you. So, the thing is, it's not just pushing against the container like this, like a balloon, right? When you blow into the balloon, it doesn't fill up because you're putting more air in there. The reason why it expands is because you have gas pushing against it, but it's not pushing like this, right? What it's doing is just little hits, lots of little hits, but it's pushing back the entire container.
Do you have flame tests, sprayers?
They are in the bathroom.
Okay.
Yeah, it's those more colored balls. So, it's pushing back just by little hits, right? Everyone in here is continually being slapped by molecules right on your face.
Just a punching bag.
They're just little, right? We don't think of it that way. We think of it as just that normal pressure because they're so small, kind of like laying on a bed of nails. Has anyone ever done that?
I haven't done it, but I know.
Wow.
Yeah. Here's the thing.
Are you trying to get Joey ideas?
Here's the thing. No. Completely safe. Completely fine.
Because there's all of those points.
Because it's multiple points all at the same time.
That's why you don't sleep on a bed of a nail.
Yeah. You don't sleep in a nail, you sleep on a bed of nails.
Yeah.
Now, same thing as like walking on gravel, right? You can walk on gravel and it's not too bad, but you step on one piece of gravel,
It hurts.
ah,
It's the Lego problem.
it's the Lego
Yes.
problem.
There's a single Lego. What's gonna happen?
Yeah. Okay.
This pile of Lego.
Guys, breathe in. Breathe in. So, that is kind of what's happening here. You're being slapped by tons of these things all at once. Now, also, that's why it kind of feels like just one pressure, one thing, instead of lots of little things. Because they're really small, they constantly are happening. But you can tell the difference between how fast they're hitting you. And I'm saying fast kinetic energy. So, can you tell the difference between a cold day and a hot day?
Yes.
Yes, your skin can tell that, right? Yeah? You know what your brain is actually interpreting?
How much you're getting hit.
How hard you're getting hit by air. Hot means you're getting hit really hard.
A lot of the time.
Cold, you're not getting hit as hard. Okay? Now it still hurts whenever it's too cold, right? That's just your brain saying like, hey, this is too cold, I got a problem, do something about it. Fix it, okay? Yeah, fix it.
Fix the weather.
But you have but the thing that's happening is, it's hot, you're getting hit by something very hard, so your brain's like, hey, this is hot. Okay?
Stop.
Yeah. Okay. We all good so far? The other reason why I like this molecular representation is because it shows that not all of them are moving at the same speed. That some are moving fast, some are moving slow, some are barely moving at all. Some are moving super fast. So just stare at one of the red ones, and you'll see that it's slow. So look at this one. So there's one. Fast. So this one's going slow, fast, faster, fast, 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 slow, fast, fast, fast. You see what I mean?
Yeah.
They're changing speed all the time because they're being bounced by everything. But also, some are very slow. Some of them actually kind of stop altogether,
Yeah.
right?
It's
There's-
fun to watch one that's going real slow and then they bump
Boom.
into a wall and then another one full shot it in, so it's
Yeah.
like.
Yeah.
It's just geometry.
Pool is, this is a lot like pool, right?
Yeah.
So, think of all of that whenever you're thinking about a gas, okay? So far so good? Okay, this also kind of helps explain some of those gas laws that we learned about before, okay? So, if something is moving at the same speed, the same mass, same speed, then it'll have the same temperature, okay? So, these blue and red, we have two different volumes of containers here, right?
Yes.
Pressure, kind of think about it in this case, is pressure is how many times it's hitting the container.
Yeah.
Are they hitting the containers at the same time?
Yes.
Yeah. So the pressure is the same. What's changing?
The volume.
Volume change, but what else changes?
The temperature.
Well, just the particle in it. Just looking at that particle, what's changing? Between blue and red.
Distance traveled.
Distance travel is greater. Speed. The red is faster than the blue, right?
Yes.
If the red is faster than the blue, the temperature is greater. What did I say about increasing the volume? Temperature goes up, right? If I decrease the volume, temperature goes down,
Pretty
right? Kinetic molecular theory makes sense, yes?
Yes.
Over here, pressure is how many times it hits the container wall. These guys are moving at the same speed, but as I decrease the volume, what's happening to the pressure? Higher, more hits, right? Lower it, less hits. Or sorry, if I increase the volume, less hits.
And that increases the temperature.
No, we're keeping temperature steady here. The speed is the same of these balls.
Really?
Yeah, it looks slower because think about it. Like, if I'm gonna move the same speed going from here to here, it looks fast. But if I'm increasing my distance, I'm moving the same speed. It's just taking longer because the distance is longer.
The temperature is the same, but pressure changes,
Pressure changes with volume.
but temperature stays the same.
If we keep temperature constant, volume will change. Remember those gas laws that we had?
You just have to keep them the same.
Yeah.
All of them, if you just kind of let things go, the pressure and temperature will change. Both of them will change, right? But if you keep temperature constant, and like in this room, temperature is not changing, right? If I take a syringe and I squeeze it, decrease the volume, pressure is going to do what? Go up, right? If I pull the syringe back and increase the volume, what's going to happen?
Pressure's gonna
Pressure's going to decrease.
decrease.
This is why. Because the little particles, they're moving at the same speed, same temperature. But if I increase the volume, it takes longer for them to hit the sides of the container. Which is why the pressure goes down.
The heading is pressure, the
Yes.
speed is temperature.
Yes.
That's all.
So pressure has all to do about hitting the side of the container. That's pressure. Yeah. A constant. That's what Boyle's law is. All right. So far, so good?
Yes.
Any other questions? Okay. Now, here's the thing. This has everything to do with temperature is kinetic energy. It's not necessarily speed. Kinetic energy is not just speed. It's speed and mass. It's both. Okay? Think about it this way. If I take a baseball and throw it at Joey, okay, 10 miles an hour. and could you catch it?
Probably the best.
Probably, right? It wouldn't, like, honestly, you wouldn't even say ow. 10 miles an hour. Think about this. A normal pitch is something like what, 60, 70 miles per hour? That's a normal pitch.
I mean, but that's like at least some amount of baseball.
The average MLB fastball is 92.3.
That's the average fastball for like Major League Baseball, right?
The best people at throwing
Yeah.
the ball.
So let's say this. Let's say this. A normal high school game would probably be about 70, right?
Yeah.
Okay, 60, 70. Okay. So if you got hit by a normal pitch, you would be saying ow. But if I throw it at a sixth of that speed, not only could you catch it, if it hit you, you'd probably be like, no.
It'd also probably be real close. Probably like.
Yeah. So there's that, right? But if I take my car and I'm rolling at 10 miles an hour and I keep going and I keep going and I hit you, would you say ow?
Yes.
You would probably not say anything because you would be crushed. The car would just keep going,
This is true.
right? Same idea. Think about like a ping pong ball, right?
Yeah.
Ping pong balls go bloody fast, right?
Yeah.
But it hits you, you might go ah, but it's not gonna.
I
It's not gonna
mean,
go.
depending on how fast it's going.
Yeah.
It's just so.
Yeah.
It's just.
Now, if I take a ocean liner and make it move that fast,
Oh my god.
a little different, right? So, do you see the difference between kinetic energy and speed?
Yes.
It's all having to do, if I roll a baseball towards Garrett at 2 miles an hour, you could stop it with your foot, right? If I had an ocean liner moving at 2 miles an hour, could you stop it with your foot? Could you stop it with your whole body? Could you stop it with everyone in this room? No. Could you stop it with a pier? No. Ocean liners just keep moving.
They get on land and they
Kinetic
just
energy
go.
is like the movement force, but the speed is like how fast it's going.
Yes, speed is how fast it's going, meters per second, right? And then, so what's force?
It's the direction it's moving.
Mass
Time acceleration.
times acceleration. Acceleration is speed squared. So, in fact, you can see it right here. Kinetic energy is mass times speed squared.
Times acceleration.
It's 1/2 that. Okay. So you won't actually have. We're not going to be calculating anything about kinetic energy. I just want you to get the concept of what it is.
This is more physics territory.
Yeah, we're getting into physics. I don't want to step in Lance's lane, but I do want you to understand the concept of this. Okay, big things have more kinetic energy if they're moving at the same speed. Okay, so let's kind of make an example out of this. Let's say that we have CO2 and NO2. Both of them are gases, right? I have 2 containers. They have the same number of gases and everything. One is hotter. One is, they're at the same temperature. We'll say same temperature. Which one's moving faster? The NO2 or the CO2?
Neither.
NO2 is moving faster. Why is NO2 moving faster?
Because a higher mass, meaning that it would have more mass to accelerate.
Other way around.
Yeah.
So they're moving at the same temperature, which means same kinetic energy. Right? So, if they both have the same kinetic energy, but nitrogen has increased mass, what is its velocity going to be doing?
To be higher.
Going down. Right?
Okay.
Make sense?
Wait, is
So-
CO2 going faster?
I'm sorry?
This one's going faster. CO2. or-
CO2.
Okay, yeah, right.
Joe. Okay.
Wait, could you explain that again?
Sure. So, kinetic energy is temperature.
Temperature.
Yes. Kinetic energy is temperature. Okay. A lot of times we say it's speed, but it's not speed. Kinetic energy is temperature. Or kinetic energy is temperature.
Kinetic energy is
We-
temperature.
A lot of times we say temperature is speed. but that's not quite true, okay? In the same way that I can roll a baseball at you at 2 miles an hour, or I can send an ocean liner at you at 2 miles an hour. Yeah,
You happen to have the spray bottles for flame test?
they're right there.
Look at the ones that are taped up in black.
I have not seen those. Listen, that I do not know. No, that is actually one of my favorite physics problems. Okay, yes.
So, an ocean liner going like to mouth,
I like
and then
the,
a baseball
I
going to mouth.
like-
The ocean
I
liner
would
has
like
more
it to be
kinetic
big.
energy.
Yes.
Okay.
Yes, very much so, right? Like, think about how much is it going to take to stop those two things.
So,
Okay.
like with potential energy, and you soft a baseball, would you have less than?
Don't worry about
Okay.
potential energy right now. Let's not worry about potential energy. Okay.
I don't like physics.
So, yeah, don't worry about potential energy right
It
now.
doesn't exist.
Key points I want you to take away. Okay. Kinetic energy, temperature. Okay. There's two parts to this: mass and velocity. Okay. So if I have two things going at the same speed, two molecules going at the same speed, but one's heavier, which one's going to be the higher temperature? The heavy one's going to be at a higher temperature.
It has more kinetic energy.
Because it has more kinetic energy.
But they're going at the same speed.
They're moving at the same speed.
Same speed, different temperature, because one's heavier.
Yes.
I'll understand it tomorrow.
Sometimes chemistry is one of those things where you have to think about it, sleep, and then wake up. Okay, so yeah, think about it like this. The reason why a thermometer works is because things are slapping up against it at a certain energy, right? What's going to hit harder? A baseball rolling 2 miles an hour or ocean liner rolling 2 miles an hour?
Ocean liner does more mass, more energy.
There we go. So, alright. So far so good?
It's a question of blast, like, is it just like, let yourself get carried by the ocean?
Say what? Oh. Well, that's the thing. You are now like one of those particles that gets hit and just keeps going.
Yeah, it just keeps going.
Yeah.
It's like when you basically get by a car, you're going.
Are we all good so far?
Yeah.
We got a bit to cover.
Yeah.
Okay? Alright, well, I don't need to do that. I'm assuming if I give you a mass and a velocity, you can calculate kinetic energy. If you have the formula on your sheet.
Mark. Yeah.
So, if you can plug in two things to get a third, can you guys do that?
Barely, but yeah.
That is, I'm assuming a certain level of math skills. Okay. All right. Now you guys remember that GIF, right? It was kind of some were moving slow, some were moving fast, but both were in the middle somewhere, right?
Yeah.
Okay.
And they were always in the
Same idea here. This is a distribution. So the y-axis here is how many molecules, okay? And this is speed on the x-axis, okay? So how many super slow things are there? Very little, right? There are very few things that are very, very slow. How many super fast things are there? Very little. But most things are
middle.
in the middle, right? Kind of makes sense. Anyone here run track? You do track?
That's weird.
So, I'm going to say this. I'm going to assume that you're probably going to be over here, right? Whoop.
In terms of the room, what?
Yeah, in terms of everyone in here, you're going to be the fastest person out of all of us.
Yes.
Most likely, right? One of the fastest. Huh? Yeah. So think about that, right? Now, I'm going to be way down here. I mean, I get winded running chasing my 7-year-old around the park.
Yeah.
So I'm going to be way down here. You're going to be up here, but the rest of the class is most likely going to be somewhere in the middle, right?
Okay.
We all good so far?
Yeah.
Right. So, that means that, like, on average, we all have a certain kinetic energy, right? Let's take the average. Don't take it, like, I'm weird. Weston's going to be a little bit weird. By weird, I mean, like,
No, Weston's just weird.
yeah. But, you see what I mean? You're not the average,
Yes.
right? I'm not average because I'm way down here. You're not average because you're way up here. Yeah?
Yes.
Average kinetic energy right here. Right? Okay. We're all good there? Cool. Here's the thing. What happens if we heat up things? Let's heat up the competition in here and get all the track, everyone in track in this room as well. What just happened to the competition? No, it didn't go because I'm still running.
Oh, you're still
I'm still running, right?
Yeah.
Which means there's still gonna be slow people, right? Now, all we did, we moved the average, but really what we did is move the distribution. Now there might be some people on the track faster than you. Don't know if there is, you could be the star, I don't know. No? So there's people faster than you. Yeah. So, they're gonna be now up here.
Yes.
You're still gonna be here, right? With the rest of the track team.
Yeah.
And then everyone else is in the middle of this. Okay? That's the thing, is that whenever you heat something up, it doesn't heat up every molecule. It heats up most, but there's still going to be slow guys. Okay? Make sense? There's still going to be some slow people. With that in mind, are there particles on the sun that are moving slower than particles on Earth?
Yes.
Very much so. Okay? Does that mean that the fastest particle on Earth is beating the fastest particle on the sun? No. But
It could be possible.
Oh,
Because there
yeah,
might
there's
just
that one apparatus that is like really hot. It gets hotter than the surface of the sun. or something.
Yeah,
Alright,
that's
then.
the thing. It's
Sure.
Because on Earth,
Alright. But naturally, let's say. Naturally.
I know.
But yeah, you get what I'm trying to say.
Yeah.
So in general, though, there is this distribution. Why is it? So this is actually just the same amount of nitrogen heated up. Okay? So at a certain temperature, at 0 degrees Celsius, we have this distribution.
Pretty slow.
But most of them are pretty slow, right? But if we heat it up, we now have this distribution. Why is it that the distribution got shorter?
Because more molecules are active.
More molecules are active. But does that mean, there you go. Does that mean that we have less molecules?
No.
No. What does it mean?
It's just
They're more spread out,
Yeah.
right? It's kind of like if I have a box and I will take that same area of box, but do this. Which one has more area? They're the same. But if I show that to my son, he's going to say, oh, this one is bigger. Have you ever done that with kids? It's freaking hilarious.
I'm more amazed that you can make one box into another box like that.
But you know what I mean.
Yeah.
It's if you go through and ask them for like, here's a glass of water and they get really long and thin,
Yeah.
versus a fat, short, they always go for the long thin one because they think it's more. Kids are dumb. All right, but you get what I mean, right?
Yes.
Okay. Couple takeaways here. No matter the temperature, will there always be slow ones? Yes. Okay. What's the number of fast ones at any given time relative to the rest?
Lower than the average.
Lower than the average, right?
Yeah.
So, you're not going around whenever you're heating something up. There's always going to be a few things that are that are super fast. Okay? There's always going to be some things that are super fast. There's always going to be like one Usain Bolt at the school. Who's the fastest? Okay, you're on track. Who's like the fastest person at school right now?
That's a good question.
Who do you think's the fastest?
Yeah.
On the team right now, there's this new kid from Southern Oklahoma. He's really fast.
All right, but yeah, blows like blows everyone away, right?
Sort of, yeah.
Yeah,
It's
let's
really close.
let's give a.
Okay, yeah. So he's like 100 meters ahead.
Thank you, thank you. Help me out here. Imagine if Usain Bolt all of a sudden visited the school.
Yeah.
What's the distribution now? Like this, and then Usain Bolt's over here,
Yes.
right? Every once in a while, you're going to get a Usain Bolt like that in the molecular scheme of things. In fact, here's a saying, especially when it comes to molecules. At high enough numbers, the improbable becomes an assurity, right? Because you have so many. If you have 1 in a billion chances, 1 in a billion chance, but you have 3 billion things, it's gonna happen, right? Yeah. So
It's like Usain Bolt on Earth. It's gonna be one.
It's gonna be one. Yeah. That's gonna come up later on. That's gonna be a very important point later on. Like a month from now. All right. Last topic. Does everyone get kind of distributions? What we mean by that?
Yeah.
The concepts behind it?
Yeah.
There's always going to be slow people. There's always going to be fast people. Most people are in the middle. Okay. Effusion, diffusion. These are a couple terms you should be kind of familiar with. Effusion means if you have a gas in a container, you have some kind of opening.
They're escaping.
Right?
That's correct.
Based on this, if you have a small opening like this, what is the big property that we need to be taken into account?
Pressure.
Pressure, but let's say all these are all under the same pressure because it's the same container, right?
Okay.
So, what else?
Number? Amount of moles?
Sure.
And size?
Size, right?
Size.
Size of the particle. So, big particles, like what's bigger, H2 or CO2? CO2 is a lot bigger. So, if you had a opening, right, H2 can fly through it. CO2, it might hit the corner, bounce out. Think of it like if you're playing pool, but you have a bunch of tiny marbles, billiard balls, ping pong balls, and you just throw them across the table. What's more likely to go in the hole? The marbles. Then ping pong balls, then billiard balls. See what I mean?
Yes.
Last one is diffusion.
They're just
The
moving.
difference between effusion and diffusion is one is not going through some sort of membrane. One's just going through a matrix of some kind. It's going through something else. So, to give an extremely gross example, if I were to pass gas,
Oh,
who's going to smell it first besides me? Front row.
yes.
Then back row.
Yes.
Why didn't it just, fill up the entire room?
Because air resistance.
Yeah, because air's in the way, right? It has to jiggle its way through a whole bunch of air, right? And that's basically what's happening. How would you go about, let's say you really wanted this gas to travel fast. How would you go about doing it? Raise its temperature.
Then it wiggles more.
It wiggles more. Or, conversely, lower the temperature of air.
Make everything cold. So it's just hot.
Mm-hmm. Use that knowledge however you see fit.
That's why it says 85.
All right, we all good?
Yeah.
Questions, comments, concerns?
That's a bit of a step. Please don't.
Air conditioning. Bathroom.
Questions, comments, concerns? Yes.
So, diffusion is going through, like in a container going through a hole,
Yeah, the way I think of infusion is like if I had a balloon and the gas, if I leave balloons out, they start losing its air, right? Why did it lose its air? It lost air because the gas was escaping through the rubber. That's infusion.
Okay.
Because it's going through the barrier.
So it's escaping from whatever.
Yeah, that's how I was thinking about it. It's just
Yeah.
Effusion means escape.
Yeah.
You know.
It's moving through.
Through like air, just normal. I like, again, the best way I can think about it is like saying like passing gas, because everyone knows that, right? If all of a sudden everyone on this side of the room says, something stinks, I'm pretty sure we can rule out Weston as the one who dealt it,
That's the cool.
Thanks.
right? Because he's way over there, right? It just makes sense.
And by the rule, it would be one of the ones who smells it.
Yeah. Exactly. So that's different than effusion, where you have like a balloon and the gas just slowly escaping the balloon. And actually, if you wanted to go through and do that, if you just blew it up with normal air, a balloon with normal air, and then let it do the whole like, have gases escape through effusion, what would be mostly in the balloon at that point? The bigger stuff. So you'd be getting rid of all the hydrogen, all the argon, all the oxygen and nitrogen. You'd be left with like CO2 inside the balloon.
Okay, so infusion is like the whole thing. It's going throughout the whole thing. Like it's through the rubber.
Yeah.
Gas. It doesn't just go out one
One
spot in the
hole.
rubber.
It could be one hole.
Like
They,
if there was a hole.
yeah, I mean if it's a big enough hole, that's just, we're not even talking about molecules anymore, right? If it's like a pinhole. But when we're talking holes, we're talking like molecular holes, tiny holes. Okay. We all good so far? There was one more thing that I missed. I was going through some things, and I realized I didn't talk about something. So let me rectify that. The thing is, how can you tell how strong your ionic bond is?
You melt it.
Sure. I mean, that would be a way of doing it experimentally, right? So let me go through and show you. For example, if I had sodium chloride versus magnesium chloride, which one of these is going to have the stronger bond?
Sodium?
Why? How many people say sodium chloride?
What?
How many people say magnesium chloride? How many people are cowards?
I mean, yeah. That's a whole different conversation.
Make a stand. So, let me ask you this. What are the things that make bonds and the two things that I'm like always taking it back to?
The pulling and the
Distance.
Distance and
distance.
charge,
Yeah.
right? Okay. Let's think about it. Charge on the sodium, 1 plus, 1 minus. Magnesium? Oh, I'm sorry. Minus, right?
Yeah.
So, which one has the bigger magnet?
Oh, magnesium.
Magnesium has the bigger magnet, which means which one's going to be stronger? Magnesium. Okay?
Still ionic?
Yeah.
Yeah.
Oh. That's strange.
So these are all ionic. I'm only talking about ionic compounds right now.
Okay.
Okay. Everything I'm going to put up there is ionic. But now, what's the strong ionic versus the weak ionic? Okay. So that being said, which one's going to have the higher melting point?
Magnesium.
All good? Okay, now let me throw another one into the mix.
Huh.
2 plus, 2 minus.
Yeah.
Bigger magnets.
Yeah, do that.
Which one's bigger? Magnesium chloride or magnesium oxide? Magnesium oxide. Bigger magnets. We needed 2 little magnets for this one, right?
Yeah.
This is 1 big magnet. We all good? What about, aluminum oxide.
Ooh, that one tastes
Very,
stronger.
very strong. This is a 3 plus. Huge freaking magnet. Right? Oh no, 6 plus. Right?
Wait.
Yeah. 2 minus times 3?
Yeah.
Actually, it should be this. Sorry, my bad. I'm getting excited.
Yeah.
So yeah, 3 plus. This is super strong. Right? We all good now?
Yep.
So now you got the size of the magnet part down. What's the other thing? Distance. Now, imagine I'm in an elevator. Okay? I want a social distance, so I want to maximize my distance from everyone else. Okay? So I get in the corner. Someone walks in, and it is a very overweight gentleman. What's the distance between me and him going to be? Very little. Okay? Okay? He gets out. Warwick Davis comes in. Anyone know who Warwick Davis is?
No
Nope. Midget.
midget.
Yeah, he did Willow, if you guys saw the movie
Oh,
Willow.
wait.
Lord.
Warwick Davis. Isn't he
Oh,
also?
he was that guy.
Yeah.
Okay, he's like Rick.
Oh, his name's
Warwick Davis. That's an academic thing, David. Or Daniel.
David Daniel.
Warwick Davis.
My man tries to not social distance. Positive spot.
So anyways, so you see what I mean though, right? Small things, we can maximize our distance more than big things, right?
Yeah.
Okay. So, that means what's going to be the stronger charge? Calcium chloride, or magnesium chloride, or beryllium chloride. Which, we're going to rank these boys. Which one's going to be the strongest charge?
Calcium.
Why calcium?
That's bigger magnet.
Bigger,
Bigger.
fatter. So it's no bigger magnet. This is 2 plus, right? 2 plus, 2 plus, 2 plus, 2 plus. So there's charge-wise, they're all the same.
Yes.
Magnets are the same size.
But calcium.
Bigger,
Yes.
which means that the distance is shorter, which means stronger thumb. Which one's next?
Magnesium.
And then finally,
Yeah.
beryllium, right? So let's go through and try this. Let's just keep these guys up here, but I'll throw in this.
Why is it MG though? Never mind, that makes sense.
Magnesium oxide.
Magnesium oxide.
Is that be first?
Yeah.
So basically, the question here is which wins out? Size or charge?
Charge.
Charge wins out. Charge goes first, and then use size as your tiebreaker. Okay? All good? Okay. Still goes back to those same things. If you run into something on the test and you're like, geez, I don't know, I can't remember.
Size wins out.
Just go back to those basic principles. How big is your magnet? How far apart is it? And then you can.
Like, how big is the answer? Like, if that's on a multiple choice, you choose the biggest answer.
No.
It sounds the most right.
No. I can guarantee there are plenty of times whenever
he's going.
where that's gonna be false. All right. Questions, comments, concerns. All right. How much time do we have left?
Like 5, 6 minutes.
5, 6 minutes. You have 5, 6 minutes to run through and do a problem on the thing. We need to vote. Oh, does anyone want the impassioned speech option? Would you like to?
I'm sorry, what?
Somebody.
The vote of the. Are we going to do all the topic questions?
There's only the 18.
Oh, no.
So anyways.
No, that's not how it works.
Do we have it in different?
Wait, so
are we?
Don't vote.
Well, yeah.
Voter apathy's a
like-
thing.
Yes, but like,
Yes, but like now.
voting is important still. I just don't want to vote for, like, it's in the independent party.
All right. So to review, you're going to vote yes if you think yes, I want more of those topic questions. They're still going to be completion, but if you don't do them, it might hurt you. Okay?
You just gotta have a wheel. Or.
Alright.
Yes, the one.
Or stay how it is right now, and I assign 1 or 2 based on how I see fit, and that's that. Essentially, right now, you're getting about 10 points a unit for topic questions, and if I do all of them, it's going to be about 30 to 40. 3 points. Except if you just don't do it. My fear is that there are plenty of people who just don't do it. So, you know, yeah. All right, let's vote. Yes.
Alright.
Yes, I want them. Raise your hand.
Yeah.
1, 2, 3, 4, 5, 6, 7. Okay? And no.